Hi, welcome back. Now today we have at hand the one of the most important topics from this chapter, actually, that is atomic radius. Okay, be very careful and very cautious while reading this, because it is very important and one question is sure in your NEET. So atomic radius is also very simple, actually. What is the radius? Radius is, in a circle, the distance from center to the periphery is the radius, right? So what we do find for atomic radius, we just assume that the atom is a sphere. We assume that it is a sphere, so the distance from the center of nucleus to the outermost shell of electrons is assumed as the atomic radius of that electron, or sorry, of that atom. Okay, so it is very simple, actually. So we have to measure the radius. How we will measure? We will take one piece of metal, we will scratch its surface so that one atom comes out, then we will take one tape and then measure. Can we do like this? We can definitely not do something like this. There are many problems in measuring, in having such a simple explanation of atomic radius, is that it is not very easily measurable. So why there it is not easily really measurable? Let's see. Look at these. The atom is too small to isolate. We cannot isolate an atom like this. It is very small and it is very hard to isolate like this atoms. Now second problem, wave mechanical model, which we have learned in the atomic structure chapter. The wave mechanical model insists on probability of finding an electron. Now probability of finding an electron is never zero at very large distances as well. So we cannot ignore, like if we take a very large distance from the atom and then we place a point, the probability of finding an electron is still there in that very large distance as well. So we cannot ignore the large distances. It will be the atomic radius would become very large. Now the atoms in the neighborhood, now we cannot isolate an atom, so what we will do, in the neighborhood there should be other atoms as well. So the atoms in the neighborhood also affect the probability distribution, right? So it affects the probability distribution and the atoms in the neighborhood as well. And now the size of the atom, it will always change from one bonding state to another. The size of the atom will always change. If we manage to measure the size like this as well, then in another state of the atom, in another environment, the size would come out to be very different from what we have taken in another environment, right? So for these problems, what we do, we have to come up with various definitions of how we can measure a atomic radius, right? So we have come up with three different ways to measure the atomic radius of an atom. Now let's look at the first method of how we can actually measure this radius, which is known as the covalent radius of the specific atom. So what is the covalent radius? It is 1/2 of the distance between the centers of the nuclei of two similar atoms bonded by single covalent bond. What we are actually telling here, we are taking a molecule. What we have two molecules, two atoms in a molecule. This can be isolated. Okay, so we isolate this molecule. We use several techniques like X-ray diffraction and other spectroscopic techniques we use, and we take a picture of this single molecule. How the picture comes out to be? It comes out to be only the nucleus, okay, and others electrons we cannot see in spectroscopic techniques. Okay, so what we have got here, we have got the pictures of only the nucleus. This is the distance, right? This is the distance between the nucleus. We take half of this distance. Half of this distance is the atomic radius of this atom. What we have done, we have taken an molecule of two atoms, we have isolated it, we have used X-ray diffraction to obtain a picture of the two nucleuses. This distance we can measure, we can measure the distance between the two nucleuses now, and we have taken the half of that distance, and we have assumed that this is the atomic radius. Okay, very easy. Now concepts, right? We have a nitrogen, another nitrogen. This is the molecule. There are 3 covalent bonds. What we will do? We will take the picture and then we will do other half, and this is the atomic radius of nitrogen. Is it true? No, never. All this is completely wrong. Why? There should be a single covalent bond between the two atoms. Nitrogen, oxygen will not do. These kinds of molecules we cannot assume as for taking the atomic radius. Okay, we have to take something which has a single oxygen bond like this. You know what this molecule is? This is H2O2. This is hydrogen peroxide. We can actually take a picture of this, so it will come out something like this, and we know that this is the oxygen. We can take the half of it, and then we can easily take out the atomic radius of oxygen, right? Now another concept, we have HCl. Okay, HCl. What we will do, we will obtain a picture, we will do half of it. This is the H atomic volume, this is the atomic radius, this is the Cl atomic radius. Is it correct? Absolutely wrong. Now in this process, atomic radius of hydrogen and chlorine would be exactly similar. Is this correct? No. What we are seeing, hydrogen is very small, chlorine is very big. If we take the half of this will definitely not be very useful for determining any atomic radius. Okay, so you should not take heteroatomic molecules for your atomic radius, right? That is why in this one it has stated two similar atoms. We have to take similar atoms bounded by a single covalent bond, right? Now you have all the concepts. Okay, but still this HCl, we can do something with it. We can do something with this HCl. This is the H, it's the chlorine. Okay, what we can do here is, now we can do something with this HCl, right? This HCl, we will take the HCl, this is the H, this is the chlorine. We will take the distance between these two nucleus, we will take the picture and then take the distance. Let this distance be dHCl, right? We can assume that the radius of hydrogen is RH, radius of chlorine as RCl. Okay, remember one formula, the distance between HCl is actually R of H plus R of Cl minus 0.09 into the electronegativity difference between these two. You don't know what is electronegativity still now, but when you come to know, this will be a very useful formula for determining the radius of one unknown atom from a heteroatomic molecule, right? We can determine the radius of one unknown atom if the other one is given, like hydrogen is actually given, the electronegativity difference is given, the distance is given, then you can easily take out, or you can easily calculate the radius of chlorine from this. This will work for any not only for HCl, any heteroatomic molecule. This will work for, but you have to make sure that there is only one covalent bond, not two. Only works for single covalent bonded heteroatomic molecules. Right, it will not work for CO2 because there are double bonds here. Right, it will not work for this, but for a single covalent bond, this is a very useful formula. Now we will take one example of this. Look at this example right here. We have given the distance between, not actually the distance, the radius, or no, this is actually the distance between the hydrogen and chlorine molecules. Okay, we have taken a picture of hydrogen molecule. This is the distance we have come out. We have taken a picture of chlorine molecule. We have distance to come out. We have calculated the electronegativity. Okay, electronegativity of hydrogen is 2.1, electronegativity of chlorine is 3.1, and we have to take out the distance between the HCl molecule. How we will do? Very simple, just apply the formula. DHCl would be equal to what? 1 plus 2 minus 0.09 into 3.1 minus 2.1. Is it like this? Will it be like this? No, completely wrong. We have to take the radius. This is the distance. What will be the radius? Will be half of the distance between the two molecules, half of 1. So radius of hydrogen will come out to be 0.5 angstrom and radius of chlorine will come out to be 1 angstrom. Now we can put it in the formula. 0.5 plus 1 minus 0.09 into difference 3.1 minus 2.1. Okay, now always remember that this should be in angstrom. Whatever you put here, this should be in angstrom, otherwise it will not work. This formula will not work. This is only calibrated for angstrom. This number will change if anything else is used. Okay, so make sure that if it is given in nanometer or if it is given in any other quantity, you make sure to convert it into angstrom and then you put this apply this formula, right? So now it is simple calculation. 1.5 minus 0.09, it comes out to be 1.491 angstrom, right? This is the distance between H and Cl. Now let's look at the second method. This is the van der Waals radius of the atom. What is this van der Waals radius? Half of the internuclear distance between two adjacent atoms of the same element belonging to two nearest neighboring molecules of the same substance in solid state. What does this mean actually? Let us assume that it is this molecule right here. Okay, this molecule is right here, another molecule is right here. So the distance between this, if we half, this is the van der Waals radius. What we are saying, this is the internuclear distance between the nucleus. Okay, done, check. Between two adjacent atoms, these atoms are adjacent, check, of the same element. This are same element, both are blue, so check. Belonging to two nearest neighboring molecules, these two are the neighboring molecules. So these are nearest neighboring molecules. There is no molecule in between here, so this is also check of the same substance. These two are same molecules, so check. in solid state. Now this should be in solid state. Okay, in solid state, if we are taking a picture with using X-ray spectroscopy or something like that, and we see that there are two neighboring molecules with no molecules in between. There are two neighboring molecules, and these two have adjacent atoms of the same kind. Adjacent atoms of the same kind, the distance between these two atoms, if we half, we get the van der Waals radius of the specific atom. Okay, remember one thing, this is not applicable for metals. Okay, you cannot tell the van der Waals radius of iron or the van der Waals radius of chromium, because it is not applicable for them. We will know the reason in the next half. Another one we have to remember is for noble gases. For noble gases, van der Waals radius is the only atomic radius that can be calculated. Why? Because noble gases do not form compounds, so we cannot find any example of molecules such that we can calculate the atomic radius in covalent radius format, in this format, because in this format we have to find a molecule of the of similar atoms in single covalent bond, but you cannot find a molecule like He molecule, He2 or Xc2. These do not exist, so we cannot find any molecules with so that we can calculate the covalent radius. So this is the only radius for noble gases. Now we have ignored metals till now in covalent radius as well as in van der Waals radius. We have said that it is not applicable for metals. Why? Because metals have their own specific radius type measurement. Okay, so what is this metallic or crystal radius? It is the half of the internuclear distance between two adjacent atoms in a metallic lattice. If you don't know, you might not know that metals actually exist in lattice. It is not like in any covalent compound or like that there are molecules of metals. Actually, or the metals actually form a single giant molecule, something like that. Okay, so this in layman terms we can put it like this, that metals, this form a lattice or a single giant molecule like this. Okay, there are no specific different molecules. That's why you cannot calculate the van der Waals radius like this, because there are no molecules of metals. So what we do in the metallic lattice, the distance, if we half it, this is the radius, metallic radius, the distance, internuclear distance between two adjacent atoms. These are two adjacent atoms we have taken in the metallic lattice. They are in a metallic lattice, we have taken the distance and they have halved it. It is the metallic radius of that particular atom. Now there is a very important relation that you should never forget, like the national anthem Jana Gana Mana. You should never forget this relation. R van der Waals greater than R metallic is greater than R covalent. Make a note and never forget that the van der Waals radius is always the largest, then metallic radius and covalent radius. Why? Because in van der Waals radius, what we have seen, two different molecules, we are measuring the distance and then we are halving, and in metallic radius we have seen the atoms are touching each other and we are taking the distance and they are halving. In covalent radius they are actually in a covalent bond, so there is an overlapping of shells of the metal in order to form a bond. So in covalent radius the radius comes out to be way less than in van der Waals radius or metallic radius. Okay, so this is the concept. You should never forget this concept. Make a note and then never forget it. Now it's time to check your concepts, right? So we have given here fluorine F2. The distance between the two fluorine atoms, the fluorine nuclei, is 5 angstrom. For oxygen it is 3 angstrom. For nitrogen it is 2 angstrom. So which atom should have the largest radius? Think about it, pause the video, think about it, and then tell. Have you got the answer? Yes, it is very easy actually. Fluorine, cut it out in the middle, 2.5 angstrom. Oxygen, cut it out in the middle, it is 3/2 angstrom, which is 1.5 angstrom. Nitrogen, cut it out in the middle, it is 2/2, come out to be 1 angstrom. So largest radius is fluorine, right? Very easy, it's fluorine. Now if you say fluorine, it will be completely wrong. Why was this wrong? Can you tell me? Yes, fluorine has 1 covalent bond, oxygen has 2 covalent bonds, nitrogen has 3 covalent bonds. As the number of covalent bonds increase, the radius will automatically, the distance will automatically decrease, but this is not at all comparable. You cannot compare the covalent radius of this three covalent bonded nitrogen with 1 covalent bonded fluorine. Okay, we have to compare it with 1 bond only. If we compare it with 1 bond, you will find out that nitrogen is actually the one which has the largest radius out of this all three. Now how will you compare this while not knowing any data, right? How will you compare? For that we will study the periodic trends. Now we have again come to the periodic table here. We will check out what are the trends of this atomic radius in the periodic table. Okay, down the group, we are going down the group, atomic radius will increase always. Okay, why it is increasing? Because as you go down the group, the number of shells is increasing. As the number of shells is increasing but the outer electronic configuration is the same, the atomic radius will eventually increase. Now if we go like this in a period, what will happen? Atomic radius actually decreases down the period. Lithium will have larger than beryllium, boron, carbon, these will go on getting smaller in atomic radius. Okay, why? Because the nuclear charge, the number of protons inside the nucleus is increasing as it is going up and it is going down the period. The number of electrons in the outer shell is also increasing as it is going down the period. So the nucleus, the positively charged nucleus and the negatively charged electrons will attract each other, right? It will attract each other. The electrons will be pulled closer to the nucleus as the charge increases. So that is the reason why the atomic radius will actually decrease as we go down the period. There is one exception, when it reaches the end of the period, suddenly the atomic radius will be the highest. The noble gases have the highest radius. So lithium will have the largest, beryllium will be smaller, boron yet smaller, carbon smaller, nitrogen smaller, oxygen smaller, fluorine smaller, but the neon will be larger than lithium as well. Like so, right? So neon will be the largest, then lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine will be the smallest one. Why? I have already discussed this concept with you. Why? Because all these radiuses that we are seeing, they are all covalent radiuses. All these radiuses we are seeing, they are all covalent radiuses except noble gases. Noble gases, the only applicable radius is actually your van der Waal radius. And what we have discussed, R van der Waal is greater than R metallic is greater than R covalent, right? So van der Waal radius, because they don't make any compounds, that is the problem. That's why their covalent radius is not actually applicable to them. We have to use van der Waal radius only. right? So that is the reason why noble gases will have the largest atomic radius in the entire period. Okay, now what I said to you, noble gases will have the largest, so I'm taking the second period. Neon will have the largest, and then just go about lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? This will be the period trend in a period, and in a group it will always increase from down below. Now there are exceptions as well. Chemistry is nothing without exceptions. So what are the exceptions that we can expect? Number one, do you remember the boron family? Boron family, bangan, aloo, gajar, in, thala, right? Boron, aluminium, gallium, indium, thallium. What is the expected atomic radius? Boron will have the smallest, then aluminium, then gallium, then indium, then thallium. As we go down the group, radius actually increases. But what is the real one? It is boron will have the smallest, then gallium, then aluminium, then indium, then thallium. What we are seeing here, this one, it is interchanged here, right? This is due to a phenomenon called transition contraction. You will learn about it when you will learn about the boron family. Just to introduce you to this term, transition contraction, this is the reason why gallium, even though it is lower in the period a group than aluminium, still gallium has smaller size than aluminium. Exception number 2 is the 3D series. This is a very important exception. I'll show you now. What is the 3D series? 3D series is right here. It's the 3D series. Okay. Now what do you expect? As we go in a period, this should increase the it should decrease. The atomic radius should decrease. Scandium should have the highest atomic radius, zinc should have the lowest. Now let's see what actually is the trend. Look at this. What is the expected trend? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, this is the expected trend. As we go down the period, it should decrease. Now what is the real trend? Scandium, titanium, this is okay, but then manganese, zinc, vanadium, chromium, copper, and iron, cobalt, nickel have almost the same radius. Okay, so there is actually no logic. It is like this. So we just have to memorize this. But how you can memorize? There is another mnemonic that I will show you. Look at this mnemonic. Sachin Tendulkar का मन जान गया वहाँ chromium copper बराबर. It does not make any sense, but it is actually effective. And Sachin is actually scandium, Tendulkar is titanium, Man is Mn, manganese, Jan is zinc, Zn, Waha, gaya is okay, Waha is V, vanadium, Waha, chromium, copper, this is easy, and barabar, iron, cobalt, nickel is barabar. Okay, so this is the trend. सचिन तेंदुलकर का मन जान गया वहाँ क्रोमियम कॉपर बराबर स्कैंडियम टाइटेनियम मैंगनीज जिंक vanadium chromium copper and then iron cobalt nickel is barabar. Okay, now we are done with this atomic radius. We have to revise this portion again and again because it is very important. All of this is very important. You should not forget any of this. Okay, if you have any doubt, you should write it down in the comments. Also like the video, subscribe to the channel, and all the very best.